हमने स्टार्ट किया था सुपरवाइज लर्निंग और इन पर्टिकुलर हमने देखी थी बाइनरी क्लासिफिकेशन. By binary classification I mean there are two classes and we want a function that actually classify the input point into one of the two classes. And by classification I mean the output should be either label 1 or label 0. And label 0 means class 1, label 1 means class 2. Make sense? And we started by linear regression model. Linear regression gave us a boundary that actually separates the two classes. Even if they are not separable, I mean it gives the best boundary based on the least square error. And the distance we use is Euclidean distance. अब regression जो है वो उसकी जो output होती है वो normally continuous होती है. तो regression model को अगर आप threshold के साथ use करेंगे, then it gives you I mean only two inputs, only two outputs, which means class 0. For example, if your regression model give you output as 0.7 or your regression model will give you the output as 0.3, you can always have a threshold that you have to learn during the training process. और उस threshold के थ्रू हम regression model को यानी regression के output को आप threshold करके limited number of labels में convert कर सकते हैं and that becomes a classification model. So regression is used for classification in that case. फिर हमने देखा था कि जो regression है in particular जो least square sense का regression हम use करते हैं, it is sensitive to outliers. Number one, number two, इसकी जो outputs हैं they are not interpretable as a score. और फिर हमने idea introduce किया था logistic regression का जिसकी outputs are actually the scores. In particular they are probabilities. So probability of being class 1, probability of being class 2. So logistic regression is again regression model. It gives the continuous output, but the output now ranges from 0 to 1, and the closer the output to 1 is higher we confident are that it belongs to class 1, and the closer the output is to 0, then we are confident that it is in class 0 with labels. Make sense? Then we covered SVM, support vector machines. The idea is to come up with a linear boundary. Again, in linear regression, the boundary was linear. In logistic regression, the boundary was linear. In SVM, the boundary is again linear, but we want to come up with a boundary that separates the two classes, the closest point of the two classes, as maximum as possible.
Yes.
So come up with a boundary कि जो दो classes हैं, so boundary के करीब एक class का जो point, जो closest point है boundary के, it should be as far away as possible. So coming up with such a boundary is the framework of SVM. इसी तरह का idea exactly logistic regression में भी है. Logistic regression जब आप boundary find out करते हैं, you actually find out a boundary that has maximum separation from all the points. SVM में difference ये है कि आप closest point से margin को या distance को maximize करना चाहते हैं. इसका फायदा ये होता है कि SVM it gives you a very sparse solution. The total number of parameters that you need is actually depends upon the total number of the closest points, the support vectors, and they are very, very small, which gives you an opportunity that you can apply the SVM model in very high dimensional spaces or with a lot of features, and that gives you natural extensions to apply the kernels. And kernel is just alleviation of your feature space to high dimensional space. Make sense? Then we move towards a variant of another kind of famous classifier which has a comparable performance like SVM, but it's very simple, which is RBF networks. The idea is to compute the radial distance or the dot product in the infinite dimensional space, and then weight that input by some vector, and then apply the linear regression model. And these kind of all are binary classifiers we use. One thing that we focus on that is important is if you increase the dimensions, if the number of features are many more, you tend to overfit if you do not have a lot of examples to train. Okay? And the idea to stop overfitting and enjoying the flexibility of the model is one idea, is regularization. By regularization, I mean the number of the total parameters that you use, they should not be very high in magnitude. So limit their magnitude or include the term कि अगर वो magnitude बहुत ज़्यादा high होना शुरू हो जाए तो उसको penalize करें. So there is a penalty term in optimization and you do that. So far we have discussed linear regression, logistic regression, SVM and RDF networks. Linear regression is just a model having least square is convex. By convex, the formulation is convex. By convex formulation, I mean the global minimum or the loss function का जो सबसे वो point जिसमें loss सबसे minimum है, that point is achievable quickly. Okay. Then, but in the case of linear regression, this is not just the convex. The solution is closed form as well. By closed form solution, I mean you can go to global minimum directly. You need not to iterate in several steps and then move. In the case of logistic regression, the formulation was again convex, but the solution was not closed form. By not closed form solution mean you cannot directly reach to global minimum, but you can start from somewhere and then iterate over some steps and then you can achieve the global minimum. In the third case in which we deploy SVM, SVM mean the problem was convex, but the optimization that we used is quadratic programming, and quadratic programming is again a sequential iterative algorithm to move towards the global minimum. And in the last case we use RBF networks. RBF networks actually reduces to linear regression once we apply the RBF function. And linear regression we already know is closed form. So we take the closed form advantage from linear regression and apply to calculate W's, and then we fix the W's and apply gradient descent to calculate the parameter in RBF network and stuff like that. Make sense? We used all the binary classifiers. We did not extend the binary classifier directly to multiclass, but it turns out that if you have a binary classifier, then you can use that binary classifier in a particular combination to achieve the multiclass classification as well. If you have, for example, 10 classes and you have a function that classifies class 1 and class 2, that can separate class 1 and class 2, you can use that function as a black box and you can achieve a multi-class classification as well. There are several techniques, and when we resolved, at the end of the day, we resolved one technique which is one versus the rest, in which आप करते ही हैं कि अगर आपके पास 10 classes हैं, for example, तो आप एक class को class 1 कहते हैं और बाकी 9 classes को class 2 कह देते हैं, and then you find out a boundary between them, and that boundary gives you the score of being class 1. अगर एक नया point आता है, ये जो function आपने learn किया है, ये आपको बताएगा कि class 1 के होने का score क्या है. फिर आप class 2 को class 1 कहते हैं और class 1, 3, 4, 5 इन सबको class 2 कहते हैं. Then you learn about it. Then you learn about it for class 3. Then you learn about it from class 4. So this is called one against the rest. हर function, for example, अगर आपके पास 10 classes हैं, you have 10 functions you have learned. The first function gives you the probability or the score that a particular point belongs to class 1. The second function gives you the score that it belongs to class 2. The third function gives you a score that it belongs to class 3 and so on. Now a test point comes in, you pass the test point from all 10 functions and compute all the scores and pick the maximum score. For example, if the maximum score occur at function 7, then the new point belongs to class 7. And that way you can achieve the multi-class classification as well. Make sense? There are blessings of dimensionality increase, which correspond to the flexibility of the model. There are blessings of dimensionality decrease, which correspond to the less overfitting or the noise removal or the unimportant feature removal and stuff. Make sense? But last time we saw that all the traditional algorithms, like if this is accuracy and this is the amount of data available, and if I plot the amount of data versus accuracy, if you have very small amount of data, your accuracy will be small, but as data increases, you try to gain accuracy because you are less overfitting, you are generalizing them and stuff. But at a particular point, in the very start, the gain will be very high, but eventually the gain will become very slow. And this is not just, this might be a scam, or you may become a logical regression model, logic, and several other traditional models. जितने भी ट्रेडिशनल मॉडल्स हैं, it is observed that they have a capacity to utilize the amount of data. यानी आप amount of data बढ़ाते चले जाएं. We have more amount of data, that's good. We have even more amount of data, training data, that is good. But there is a capacity. कि इसके बाद अगर यानी SVM has a capacity कि इतना data ये use करेगी तो it will gain accuracy, but after that it will not utilize the data जैसा कि डेटा को पहले ग्राफ में यूज कर रही है. जैसे जैसे अमाउंट ऑफ डेटा आप एक पर्टिकुलर कैपेसिटी से ज़्यादा बढ़ाना शुरू कर देंगे, the utilization of the data becomes very very small in the traditional models. Make sense? And one kind of thing might be that the models are too simple. When the simple models are there, if the models are simple, they have less parameters to learn, and less to learn very few parameters. You need not many more data points. Make sense? अगर आपके पास models बहुत simple हैं और आपके पास data points बहुत ज़्यादा हैं, तो very few data points they will be able to compute the parameters, and you may have to come up with very complicated models to utilize more and more data. With very complicated model, I mean you have a lot of parameters to estimate. Yes, ma'am?
Yes.
So it turns out that these might be the graphs and stuff like traditional classifiers. By traditional classifiers, I mean the classifier neural network is not included here. Okay, the other classifiers, they have this kind of capacity, and it is observed capacity. That after a certain amount of amount of data supplied, if we supply much more data, for example, if your data points and 30,000, then SVM has a particular accuracy on a particular data set. If I increase the 30,000 points to let's say 3 lakh, the accuracy does not gain much. It is improved, but not that improved. जितने की amount of data के लिए लिहाज से होनी चाहिए. जी आते हैं. It turns out that neural networks, spelling इसके क्या होते हैं? Neural networks. It turns out that neural networks, they actually have very good property of utilization of the data. If you supply more and more data to it, it will utilize and will gain accuracy. One reason is because the neural networks, they are very complicated. Complicated in a sense that they have a lot of parameters to tune. So they have a lot of parameters to tune. By parameter tuning, I just take a simple example. For example, I have the following equation: W1x1 plus W2x2 plus WKxk. Let's say this is equal to 7. Okay. And I have another. So this is 1, 1, this is 2, 1, this is 3, 1, this is x 2, x 1, 2 plus W2 x 2, 2 WK x k2 is equal to 2 and so on. To determine these number of parameters uniquely, I need a lot of points. For example, this is 1 point. This is 1 point. I need another point. I need another point, another point. If I want to estimate a lot of, if number of parameters are too much, too many, I need a lot of parameters I need a lot of points to uniquely identify these parameters. They are. In neural networks, we will see shortly that the number of parameters are actually very large, very, very large. So they are always data hungry. You supply more and more data, they utilize that well and still say, okay, is there any more data? The question here might be कि यार अगर मॉडल को कॉम्प्लिकेट करने से या नंबर ऑफ पैरामीटर्स बढ़ाने से ही डेटा यूटिलाइजेशन होती है, तो आर देयर अदर वेज कि हम डेटा मॉडल को कॉम्प्लिकेट करते हैं और उसमें नंबर ऑफ पैरामीटर्स को एक्सटेंसिवली बढ़ा दें, क्या यूटिलाइजेशन ऑफ डेटा हो जाएगी? द आंसर आई डू नॉट नो, बट इन द केस ऑफ न्यूरल नेटवर्क द एक्सटेंशन is very straightforward and systematic. Yani the increase in the number of parameters is just adding one more layer to it, and then increase in the parameters is just adding another layer to it. And this addition of parameters is so systematic that your algorithm does not get complicated. जो algorithm है, जो parameter estimation का algorithm है, it becomes the same, it stays the same, and the extension and removal, that is quite systematic. This might be one reason of success of this, and the second reason is they are working. I mean, they are working. Make sense so far? अब यहाँ पर कुछ ज़रूरी सवाल हैं या ज़रूरी बातें हैं जो मैं न्यूरल नेटवर्क का एल्गोरिथम एक्सप्लेन करने से पहले करना मुनासिब समझता हूँ। एक ये कि न्यूरल नेटवर्क एक क्लासिफायर है, ठीक है? It will take a data point and it will give you a label at the end of the day. Inside it there is a classifier जिसको हम न्यूरल नेटवर्क बनाते हैं, सही? It is famous, it is successful, and all its performance is empirical. इसकी performance की guarantees जो हैं वो theoretical नहीं हैं, they are empirical, they are working. Theoretical guarantees शायद हो भी नहीं सकती हैं, उसकी वजह ये है जो थोड़ी देर बाद मैं बताऊंगा आपको कि अगर मैं नंबर ऑफ लेयर्स एक से ज़्यादा कर दूँ, यानी इफ आई हैव अ न्यूरल नेटवर्क विद एटलीस्ट 2 लेयर्स, देन द प्रॉब्लम कि मैं एग्जैक्ट वो वाले वेट्स लेके आऊँ जो ग्लोबल मिनिमम अचीव करेंगे या जो ट्रेनिंग एरर को ज़ीरो करेंगे, दिस प्रॉब्लम इज़ NP हार्ड, एंड दिस प्रॉब्लम इज़ NP हार्ड टू द लेवल दैट अगर मेरे पास 3 न्यूरॉन्स हों और 2 layers हों, the problem is still NP hard. Which in layman terms is this: solving a neural network in the hope of achieving the best solution. That hope is hopeless. और उसकी वजह शायद ये है कि ये जो NP hard problems हैं, NP complete problems हैं, people are working on that from decades. And it turns out कि अगर कोई ये प्रॉब्लम सॉल्व कर देगा, then there are several other famous problems जो कि सॉल्व हो जाएंगी, और बहुत अरसे से ये सॉल्व हुई नहीं है। इसलिए ये होप कम है कि कोई न्यूरल नेटवर्क का ऐसा एल्गोरिथम लेके आ जाएगा जो इसका ग्लोबल मिनिमम अचीव करेगा। Having said that, the optimization problem is non-convex. It is the global minimum is not achievable in finite amount of time, or at least in polynomial time. People have observed कि जो एल्गोरिथम हम डिवाइस करेंगे ऑप्टिमाइजेशन सरफेस के ऊपर मूव करने के लिए, वो अगर लोकल मिनिमम में ले जाए, ग्लोबल मिनिमम तो पता ही नहीं चल सकता ये जो मिनिमम आया है ये ग्लोबल है या नहीं है, ये पता नहीं चला सकते। इफ इट इज लोकल मिनिमम फॉर एग्जांपल, एंड इफ इट इज सफिशिएंट, वी आर गुड टू गो विद दैट। सो द प्रॉब्लम अचीविंग द ग्लोबल मिनिमम, आई मीन दिस इज नॉट द गोल ऑफ द scientists that are working in this. Coming up with an algorithm that achieves a local minimum efficiently, that's actually the goal. Yeah, I mean, at the end of the day, you are achieving local minimum, or whatever you have achieved, you have no guarantee whether it's global or not. So let's come up with the algorithm that achieves the local minimum faster, and that's what the community is working on. और अगर इसके काउंटर पे आप ये आर्गूमेंट लेके आए कि नहीं ग्लोबल मिनिमम को अचीव करने का एक एल्गोरिथम डिजाइन करना चाहिए, then वो कहते हैं NP hard, should we do that or not? So whatever algorithm I will describe here, that's approximation algorithm, and people are coming up with tuning and engineering kind of stuff that takes your algorithm, I mean, less time and achieve to some minimum that is feasible. Make sense? For those who are interested in finding out the decision problem, that is NP hard. Is following the decision problem, that is the statement. The decision problem is in the general settings. Is there a neural network that, given general number of training examples, the neural network does not make a single error on a training example? this decision problem is ambiguous. Make sense? For those who do not understand this decision problem, that's okay. I just spoken this for specific. Okay. Yes.
अगर मॉडल बहुत ज़्यादा पैरामीटर्स ले रहा है तो ओवरफिटिंग ना करना।
Yes. So yes, overfitting is there. So there are ways to avoid overfitting in neural networks, and we will discuss. Three popular ways. One way is to add a term which is weight decay, that we already have added in other models. That is the regularization on the weights. The other is we will see the stochastic gradient descent in a moment. The other thing is start the gradient descent, but stop it early. Do not let it go, and that will stop overfitting. The third thing that stops overfitting is dropout. Dropout means when you have a lot of neurons, you have a lot of weights. Just kill randomly some of the neurons in one iteration, then kill some of the neurons randomly in another iteration, and move like this. So in one iteration, the total number of parameters is lesser than what have shown the and it turns out that these kind of techniques, they actually reduces the complexity of the model and add a regularizer term, and the overfitting is not there in a sense कि अगर इनके अलावा करते तो overfitting की बात है, ठीक? So I'll explain the overfitting because this is the first thing that should come into your mind. यार जब parameters बहुत ज़्यादा होंगे, the model is highly flexible. I can mold the model in wherever I want. That means overfitting will be there. Make sense? So there are ways to stop overfitting in neural networks.
सर जब हमारे पास ऑलरेडी ऐसे मॉडल्स हैं जो हमें ग्लोबल मिनिमा दे रहे हैं,
Yes.
जिसमें हम मतलब लोकल के मुकाबले में ग्लोबल जो है वो हमारा उससे ज़्यादा प्रूफ पॉइंट है, तो फिर न्यूरल नेटवर्क जब ये लोकल मिनिमम दे रहा है तो हम इसकी तरफ क्यों मूव कर रहे हैं?
Because it is more flexible. It can learn more. जो models आपको अब तक for example SVM, logistic regression and these kind of models जो आपको दे रहे हैं, they have less. आपने उनकी कैपेसिटी लिमिटेड कर दिया. फॉर एग्जाम्पल SVM में आपने लिमिट कर दिया कि यू हैव टू लर्न लीनियर मॉडल. दैट्स अ लिमिटेशन ऑन द मॉडल यू हैव पोज्ड. मेक सेंस? एक लिमिटेशन आपने पोज कर दी, उस लिमिटेशन के अंदर रह गए जो भी कॉस्ट फंक्शन आपने बनाया है वो कॉन्वेक्स है, उस लिमिटेशन के अंदर आप ग्लोबल मिनिमम ढूंढ सकते हैं. लेकिन आपने उसकी जो फ्लेक्सिबिलिटी है उसको स्टार्ट में ट्रिम कर दिया था. यू डिड नॉट अलाउ इट टू लर्न मच मोर. Making the problem, in this particular case, you made the problem non-convex, very complicated. आपने problem build करते हुए ये नहीं सोचा कि मैं इसको solve कैसे करूँगा. At that time, you allowed it to learn whatever it wants to learn. And then you focused on, oh, this is very complicated, how can I estimate the model, estimate the parameters. But by designing the model, you design the model that has much more flexibility than, flexibility means they have much more learning capacity than the model so far.
सर लेकिन उतना ही देर हमारे पास मसला भी तो होगा कि नॉइज जितनी उतना ही नॉइज कवर होगी उसके अंदर. हम आज तक ये करते रहते हैं यार किसी तरह से नॉइज बचाएं अपने मॉडल को, उतनी फ्लेक्सिबिलिटी इसी के ऊपर हम इम्प्रेस करते हैं यहाँ तक. तो आज उसी चीज़ को हम वर्क करेंगे और फिटिंग डालने नॉइज भी कितने होगी अंदर, एफिशिएंसी भी कैसे आ रही है.
जी, इसमें एक्चुअली न्यूरल नेटवर्क्स, इन पर्टिकुलर डीप नेटवर्क्स, ये वर्क ही तब करते हैं, रिकमेंडेड ही तब होते हैं व्हेन यू हैव इनॉर्मस अमाउंट ऑफ डेटा. तो जब आप, मैंने लास्ट टाइम भी बताया था, इफ यू हैव लॉट ऑफ डेटा, नॉइज विल रीच आउट. I mean, one way, and actually the only way to suppress the noise is to get more points. In this particular case, you have a lot of data. You have a lot of data available. It just turns out that your traditional algorithms, they are not utilizing the data very well. Although they give you global minimum, in those settings, जिन settings आपने उसकी deploy कर दी. अब आप flexibility दे रहे हैं model को, data बहुत ज़्यादा है, and this is the model that is utilizing the data very well. Because the data is, I mean, the number of data points is very, very large, and only then the deep learning is recommended. The noise will be averaged out. Make sense? And there are tricks and hacks, engineering hacks, to reduce the noise during the learning time. One is called batch norm and other stuff. People came up with over time that if you do this kind of update in your algorithm, the noise will be suppressed out, and if you do this kind of update, there are engineering hacks to reduce the noise in the data. having said that, all these tricks are engineering tricks. I mean, the results are empirical. They have applied these kind of models on large amount of data sets, on different data sets, and empirically they got good results. Make sense? So there is no practical justification to do this or to not do that. Okay, so here is the architecture of a neural network. First, let me explain the architecture. I'm just taking one example as input for now. So again, I have one example, x1i, this is the ith example. x2, this is the ith feature. And then we have xdi, this is the dth feature, and this we need for the bias term, okay? And this is a neuron. So this goes inside here, this goes inside here, this goes inside here, this goes inside here. Every input feature is multiplied by a real number called the weight. For example, this is multiplied by 0, this is multiplied by 1, this is multiplied by 2, and this is multiplied by d. All these are multiplied by this. And here we have a sum, let's say j raised from 0 to d, wj xi xj. This is simply a dot product. अगर हम इस फीचर वेक्टर को अगर हम इसको सिंपली कहते हैं xi, मैं हैट नहीं लगा रहा because this one is always there. If this is the xi ith data point, and this vector w is actually w0, w1, wd. If this is w, then this particular number is simply w transpose xi.
Yes.
Make sense?
Yes.
Yes, no?
Yes, sir.
Just to explain, I'm writing this number as z. This is z. Z is simply dot product of this and that, which means every input feature is multiplied by a weight, and then all these multiplications they added up, and this number comes in z. Okay. Then something happens to z, which I'm calling gz. Some function is applied on z, and that function is nonlinear. I will explain why a nonlinear function is required. Some function is applied on z, and z is already a real number. Gz is a different real number applied on g. Z is a real number, gz is a real number, and that g gets out. Make sense? And I'm calling that gz, that is coming out as a. Make sense? This is one neuron. This is one neuron. This is one input feature, this is one neuron. And again, xi is 1, x1i, xdi, and w is simply w0, w1, w, and z is w transpose xi. Make sense?
Yes.
And this, so gz is a. So a is g of z. G is some function. I will explain this one. For now, you can assume this g is just a sigmoid, which is g of x is equal to 1 over 1 plus e raised to the power minus x. And this function actually ranges from 0 to 1. Okay? So this function, this range, 0 to 1. Okay. This is one neuron. I can have another neuron. By the way, this one neuron is simply the logistic regression model. This alone is a classifier, and that is called logistic regression. We have seen it. You threshold this A from 0.5 or whatever threshold you like, and that is the complete binary classifier. Make sense?
Yes, sir.
Let's have another neuron. Let's name these neurons. Let me name this neuron as neuron 1, and then let me name this as Z1, and let me name this as A1. Okay? Let me name this neuron as neuron 2. Okay? So whatever here, it will be Z2 and GZ2, and whatever जो कि बाहर निकलेगा that is A2. Make sense? अब होगा ये जो सारी इनपुट इस न्यूरॉन में ली है, एग्जैक्टली वही सारी इनपुट आपने यहाँ पे लेनी है. So this is complete neuron like the previous one. लेकिन इसके weight अपने होंगे. So let me call this weight as W01, W11, W21, WD1 for weight of neuron 1. Now the weights of neuron 2 are W02, W12 and so on, so WD2. Make sense?
Yes, sir.
So Z2 is so let me call this as WI, WJ, this and that. So ZJ is WJ, next side, and IJ is CJ. So far so good?
Yes, sir.
Then we have another neuron, might be a third neuron. And the third neuron will be having weights W03, W13 and so on. And it will give us A3. Make sense?
Yes.
Yes, no?
Yes.
So this is then we can have a neuron here. That's a fourth neuron, but this particular arrangement, then this input will not be fed to this. Actually, the output of this will be fed to this as input. This will make this as the first neuron in the second layer. This is the second layer that has been started. Make sense? And second layer means this input is going in, this input is going in, this input is going in. Output of the previous layer acts as input to the next layer. And then we have to supply 1 for the bias. Yes? Make sense? ये 1 हमने देना है. Now these are the features for this neuron. Clear? This will compute Z1. Let me call it layer 2. Layer 2. ये layer 1. All these are layer 1. This is layer 2. First of layer 2. Make sense? Again, it will pass through some G. And it will give me A of layer, this was of layer 1 again. 1, 1, 1. This is of layer 2. Make sense? Yes, no? There might be another neuron. And so all these are, this A1 is fed to here, this A1 is fed to here, this A3 is fed to here, with different weights again. With different weights. And this will give me Z. 2, 2, and this will give me A 2. And there might be a neuron here.
सर लेकिन जो X है हमारे पहले शिफ्ट में वो तो हमारे डेटा पॉइंट्स थे लेकिन जो A1 जो A है हमारे तो कुछ ना कुछ उसने रिजल्ट निकाला ना कि किस क्लास में लाई कर रहा है उसने नंबर निकाला हुआ है
एग्जैक्टली.
तो इसके ऊपर आप क्लासिफाई कैसे इसके ऊपर
मैं अभी अर्ज करता हूँ. मैं इसकी फॉर्म पास अभी अर्ज करता हूँ कैसे करें. So this and then this is obviously and then a 1 there. 1 is coming. So this is W0, 1 of layer 3. This is W1 of neuron 1 of layer 3. Okay? And then you come up with this again, something like that. Yes? This is a graph. सही है? और ग्राफ के बिल्कुल स्टार्ट में बाय द वे ये टैग है यूनिडायरेक्शन का ग्राफ है. इसके बिल्कुल स्टार्ट में आपने ये नंबर्स हैं जो आपने देने हैं. सो द थिंग्स दैट यू नीड टू बिल्ड दिस ग्राफ फ्रॉम बिल्कुल जब स्टार्ट करने लगे द इनपुट पॉइंट दैट यू नीड. सो दिस D+1 numbers that you need. Second thing that you have to decide before building this graph is what function g will you use. Say, for example, if you use this function, then you must know okay, ये function use करेगा. This is not a function that will be learned automatically. You have to supply this function, and this function is called an activation function. Say, this function, and you can use different functions for different neurons. For simplicity now, I have used the same function overall, but you can use different functions for different neurons, different functions for different layers, but you know, whatever activation function or set of activation functions you are going to use, you should know them beforehand. Clear it? And then you are good to go. Then you are good to go. Once you have available what function g you are using, and once you have available what is the input, you can compute this number as a final number. And if this number is, for example, thresholded by 0.5, it is of class 1, otherwise it is of class 0. So this input point can be classified if this point is fed to this network, and then this is thresholded. And let me explain how. फर्स्ट करें आपके पास ये W's यानी weights for the first neuron. ये पहले न्यूरॉन के weight कितने हैं पता? How many weights are there for the first neuron? D plus 1 starting from W0.
Yes, sir.
How many weights are there for this neuron?
D plus 1.
How many neurons? How many weights are there?
D plus 1.
How many weights are there for this?
Layer 1 में वो है.
So जितने न्यूरॉन पहले थे plus 1.
Plus 1.
And so on. So how many weights are there? 3. That's it. फर्ज करें मुझे न्यूरॉन 1 के weights पता है, यानी मुझे D plus 1 numbers पता है. फर्ज करें. Can I compute this output?
Yes, sir.
Yes. अगर मुझे GB पता है तो.
Yes, sir.
I will simply take the dot product of the input point. Input point मुझे given है. मुझे किसी ने कहा यार ये point classify कर दो. 0 1. Input point मुझे given है. And it just so happen कि मुझे ये weights पता है. Let's say I'm assuming I know the weights of neuron 1. Okay? And then I can compute this number. Yes, no.
Yes,
I can compute this number. Just take the dot product of weights and this, and then apply this function on that. And this function is also available freehand. ये नंबर निकल आएगा. अगर मुझे न्यूरॉन 2 के सारे वेट्स पता हो, जो D plus 1 नंबर्स हैं लेकिन फर्क नंबर्स हैं. न्यूरॉन 1 के कोई फर्क नंबर है, न्यूरॉन 2 के कोई फर्क नंबर है. अगर मुझे ये भी सारे वेट्स पता हो, अगर पता हो, अगेन कंप्यूट दिस नंबर.
Yes.
Yes, no.
Yes.
अगर मुझे न्यूरॉन 3 के सारे वेट्स पता हो, I can compute this number. Yes, no.
Yes, sir.
अगर मुझे लेयर 1 के सारे वेट्स पता हो, I can move to layer 2.
Yes, sir.
Yes, no.
Yes, sir.
अब अज्यूम करें कि मुझे इस न्यूरॉन के सारे वेट्स पता है. बिल्कुल. इसके कितने वेट्स हैं टोटल? 4. अगर मुझे ये सारे पता है, तो मैं ये नंबर निकाल सकता हूँ.
Yes.
क्योंकि ये नंबर मैं कंप्यूट कर चुका हूँ.
Yes, sir.
इसको मैं मल्टीप्लाई करूँगा कॉरस्पॉन्डिंग वेट से, 1 को मल्टीप्लाई करूँगा वेट से, इसको मैं ये नंबर निकालूंगा.
Yes.
Yes. Similarly, अगर मुझे इस न्यूरॉन के सारे वेट्स पता है, I can compute this number.
Yes.
Make sense?
Yes, sir.
Yes, no.
Yes, sir.
If I know the weights of layer 1 and the weights of layer 2, I can move to this thing. I can
Yes.
move to the next layer. Yes, no.
Yes, sir.
अब फर्ज करें मुझे इस न्यूरॉन के सारे वेट्स पता है. By the way, इस न्यूरॉन के 3 वेट्स हैं. Let's say मुझे पता है. Then I can compute this number.
Yes, sir.
And then I can threshold it. Make sense?
Yes, sir.
अब लर्निंग क्या है? लर्निंग ये है, वो वेट्स ढूंढ के लाओ. वेट्स पता नहीं है, वो वेट्स ढूंढ के लाओ जो क्लास 1 के इनपुट पॉइंट्स में जो नंबर जनरेट करें एट द एंड को 0.5 से बढ़ाओ, और वही वेट्स क्लास 0 के जो पॉइंट्स हैं उनके लिए जो लास्ट वैल्यू जनरेट करें वो 0.5 से छोटी. लर्निंग दीज वेट्स इज कॉल्ड ट्रेनिंग अ न्यूरल नेटवर्क. मेरी बात समझ में आई? ये वेट्स पता नहीं है, ऐसे वेट्स लेके आओ, ऐसे वेट्स लेके आओ, यानी न्यूरॉन 1 के वो सारे वेट्स, न्यूरॉन 2 के वो सारे वेट्स, न्यूरॉन 3 के वो सारे वेट्स लेके आओ, न्यूरॉन 4 के वो सारे वेट्स लेके आओ, न्यूरॉन 5 के, न्यूरॉन 6 के वो सारे वेट्स लेके आओ. That map the vector of class 1 to class 1, and the same weights are responsible of mapping the vector of class 0 to 0. learning these weights. To learn these weights, we need training data. We need a lot of data along with the labels. Yes.
सर इसके अंदर हम ये लेबल्स हैं वो कहाँ पे किस जगह पे बता रहे हैं कि ये पॉइंट क्लास 1 का ये पॉइंट क्लास 2।
मैं अभी ट्रेनिंग पे आता हूँ, मैं अभी सिर्फ मैं इस बात पे आया हूँ कि अगर weights पता हों तो at the end you can achieve this value and you can threshold it and you can come up with the label of the test point. Training करनी कैसे will see that. Make sense? ये weights निकालने कैसे will see that. लेकिन अगर weights पता हो then this is a classifier. एक test point आप दें, it passes through a series of steps and eventually it will give you a label for that test point. Yes. So it's a classifier. Yes, no?
Yes, sir.
Make sense? यहाँ पे एक क्रिटिकल सवाल का मैं आंसर करता चलूँ और उसके बाद मैं इंशाल्लाह ट्रेनिंग पे आता हूँ कि इसकी फिर ऐसे वेट्स निकालते कैसे हैं, हाउ टू कम अप विद दीस काइंड ऑफ वेट्स। मेक सेंस? अगर आपको ये नेटवर्क क्लियर है। और बाय द वे पहली लेयर में कितने न्यूरॉन्स होने चाहिए? आई डोंट नो। कितनी लेयर्स होनी चाहिए? आई डोंट नो। कौन सा एक्टिवेशन फंक्शन यूज करना चाहिए? आई डोंट नो। ओके, now there are practitioners that recommend certain things कि there are architectures कि यार पहली लेयर में इतने रखें, दूसरी लेयर में इतने, और आपके डेटा पॉइंट्स इतने हैं तो टोटल नंबर ऑफ लेयर्स अगर इतनी रखें एंड एक्टिवेशन फंक्शन ये यूज करें, it happens कि this combination works. Make sense? But on your data, on your particular data, which combination is going to work, or you have to discover your own combination, is again open. This is very good thing to start with some build architecture, some build recommendations, and then see how much you have gained in terms of accuracy. If you have not, just tune it or change it. Clear? This is engineering. Let's see how to decide the number of layers, how to decide the number of neurons, stuff like that. Okay, why do we need a function g here? The question is, when z is computed this way, first of all, why is z computed this way? The last time हमने देखा था, this is simply a linear model, and having a lot of linear models means combining a lot of lines, and using a lot of lines you can achieve any non-linear boundary. Make sense?
Yes, sir.
So that's why this gives you a linear boundary for one neuron, and several neurons and networks of these is actually combining a lot of lines together, taking their intersections and so on. So using a lot of lines and their intersections, you can cover a boundary that is highly nonlinear. And if you want to cover more nonlinearity, add more neurons. Make sense? Yes, no?
Yes, sir.
जी मैं दोबारा बता देता हूँ।
ये अब जिस वो जो हमने एंड वगैरह की कंडीशन लगाई थी, ये वो जी था।
Yes. मैंने लास्ट लेक्चर में ये एक्सप्लेन किया था कि one neuron is actually one line. Okay. It gives you one boundary. You can combine two neurons by having ands and ors together. Ands, ors, logical gates, X, or whatever. So combining two lines means वो पॉइंट जो इससे नीचे है and उससे ऊपर है, उसका लेवल ही होना चाहिए. Now combine three lines. Now combine having more and more lines, you can combine these lines in a way to achieve a boundary that is highly non-linear.
Yes.
Make sense? And I mean, there is a proof you can, having sufficiently many lines, you can achieve any function. Obviously, for any just take an example of circle. To achieve circle, you need infinitely many lines, but given enough lines, you can achieve any. Okay. Why this function is there? It just turns out that if this function is not there, then, and this function is not there, then Z1 is simply W1 transpose X. Yes? And then there are a lot of Z's. Z1, Z2, Z3 and stuff. Make sense? And then, अगर मैं Z's का vector बना लूँ, Z1, Z2, Z3, and I multiply it with W transpose, and that gives me Z for the next stage.
Next layer.
Then these two can be cascaded together to become W2 transpose, W1 transpose X, and that is my Z in this level.
Yeah.
And at the end of the day, it will become a linear regression. It's a linear regression at the end of the day. अगर ये function मैं बीच में employ नहीं करता, और अगर ये फंक्शन लीनियर भी हो तब भी एट द एंड ऑफ द डे यू एंड अप हैविंग स्टार्टिंग फ्रॉम अ पॉइंट and ending at the end, all these things, all inside thing is a matrix multiplication, which means x is mapped to the label by a matrix multiplication, which means it is again a linear regression. So in particular, I want this function to break the linearity, to avoid this cascading,
अच्छा
and then it will be learning something better than linear regression, not otherwise. ये समझिए, दोबारा से देखें, अगर मैं g फंक्शन नहीं लेता तो एक लेयर से दूसरी लेयर पे जाने के लिए मुझे दो मैट्रिसेस मल्टीप्लाई करने पड़ेंगे इन केस के इनपुट x को. सो इनपुट x टाइम्स द फर्स्ट मैट्रिक्स एंड दैट इज द आउटपुट. इसको मैं एक और मैट्रिक्स से मल्टीप्लाई कर देता हूं, दैट इज द आउटपुट ऑफ द थर्ड लेयर. अब ये मैट्रिक्स 1 और मैट्रिक्स 2 इनको मैं आपस में मल्टीप्लाई करता हूं, दैट इवेंचुअली इज द मैट्रिक्स. So going from input to layer 3 or 4, it is just a matrix multiplication. अब जरा देखें, going from input to last layer is eventually a matrix multiplication. So and at the end होगा क्या? Your label y is equal to wx.
W
Make sense? And this is exactly the linear model.